Hi dear students, in the previous class we have started a new chapter, that is laws of motion. Okay, so in this laws of motion, mainly our target is to learn Newton's laws of motion. Okay, so here we just want to understand by which law a body moves. In the previous class only we have discussed and we have learned that for motion the main important thing it is needed, that is force. It is predicted by Galileo and later it is come by the law of Newton. We have learned Newton's first law of motion. We have already done it in the previous class. So what is told in Newton's first law of motion? It is told that if a body is at rest, the body should remain at rest. If a body is at motion, the body should remain at motion in same direction and same speed until an external force is applied on it. Okay, so until or unless an external force is applied on it, in which state the body is there, it just try to be in same state. And now from Newton's first law of motion we have learned two new things. First one is definition of force. What we have learned by that? That force is such an external agent by which we can able to make change in a state of a body. Either it can be a state of rest or it can be a state of motion by that external agent, that is called force. So earlier also we defined force, but here we define it elaborately. Next, idea of inertia. In this law we have seen one thing, that if you have not applied force to a body, the body will just try to remain in a same state where it is. That means it is a property of a body that it just try to be in same state of motion. Either it is rest or in motion. It just try to be in same state. That is known as inertia. We have also learned there are two kind of inertias are there. In the previous video I have shown three kind. So in many book it is written two kind, in many book it is written three kinds. So generally we have taken two types, that is inertia of rest and inertia of motion. So up to this we have learned, we have discussed about the examples that we will not do here. We have already done it in the previous video. Now the question has come, what thing has left? We have done almost all the thing. No, one thing is left. On which thing that inertia of the body depends? That is not told in the previous video. So here I have told inertia of a body depends on mass of it. Inertia of a body depends on mass of it. That means more mass, more inertia. Example, assume a wooden box is kept in one place and a same kind of box which is made by iron, that is also kept in one place. So to lift or to move wooden box or to move that iron box, which one is harder? We all know it is harder to move a iron box because the mass of the iron box is more. So as the mass is more, so we can say the inertia of rest of that body is more. Similarly, assume a cycle is coming with towards you with a speed. Assume a car is coming towards you with the same speed. Which is easier to stop? Definitely, or which is easier to make your direction of motion change? You will definitely tell, say, it is easier for a cycle to change the direction or to stop. It is difficult for a car. And whenever I am talking about stop, I am talking about that we want to stop it by applying force from outward, not by the brake or something like that. So definitely it is easier to stop a cycle rather than a car. So simple thing, for the car, as the mass is more, so definitely here much force is needed to change its inertia of motion. So more the mass, more the inertia, that we have learned. But one thing is left, that is force. Now you can ask, sir, we have already defined force. What is the problem with that? Yes, we have defined force. But whenever we have to define a physical quantity, one another thing has come into our mind. That is measurement. We can able to define force by Newton's first law of motion. But how can we able to measure it? Because that is also a very important part. Without measuring a physical quantity, it is useless for us. And for that thing, the second law has come. So the main target of second law is to measure the force. The main target of second law is to measure the force. Now, there is a problem. What? So to measure something, we need some tools. If anybody asks you to measure the length and breadth of the board, you ask for a measuring tape or you ask for a scale. So without tools, we cannot able to measure. So here, to measure the force, we need some tools. What are the tools? So for that, the tool has come, a tool we have taken, or it is taken by Newton, that is linear momentum. Now you may ask, what is it, sir? See, it is a physical quantity, but one thing it is not discussed, that whenever we are talking about physical quantity, we have already learned it in the first chapter. I have made a video for the first chapter, and I'll just suggest go through that video and you will get what is physical quantity and what are the properties of it, how we can able to measure it, etc, etc. But when we are talking about physical quantity, anything that can be measured. Now example, mass, length, that we can able to measure. So these are physical quantity. That thing you have learned from the class 6 or 7. But problem is here, there are two kinds of physical quantity. Which one? It is known as natural physical quantity, just like mass. If you measure or not, a body should have mass. Just like if I have told that pen, okay, if you measure or not, it should have a definite mass. If you measure or not, it should have a definite length. Okay, so these are known as natural physical quantity. But if I just want to form a physical quantity, that physical quantities are known as derived physical quantity. Example, we know mass of a body, and if the body moves, the body should have a velocity. Means if a body is in motion, it should have a velocity. Now mass, it is a natural physical quantity. Velocity, it is also very much natural. But what we have done, we have taken a product of mass and velocity of a body is known as linear momentum. What is it? Now if we multiply mass and velocity, then it will be converted into another physical quantity, that is linear momentum, which is denoted by P. P equals to m into V, where m is for mass, V is for velocity. Okay, so this is a derived physical quantity. We have derived to measure force. So we know for measuring something we have made different kind of tools here also to measure the force, because the idea of Newton's second law of motion to measure the force. So to measure it, we have derived a new physical quantity which is known as a linear momentum. If I am talking about its characteristics, it is a vector quantity. It is a vector quantity. That means it should have both magnitude and direction. Now, if I am talking about the unit of it, so as I am talking about a new physical quantity, so it should have a unit. Number 1, SI unit. So it is arrived for making the product of mass and velocity. So the unit should be the unit of mass in SI, that is kg, and unit of velocity, that is meter per second. So its SI unit is kg meter per second. If I am talking about the CGS unit, okay, so CGS unit of mass is gram and CGS unit of velocity, it is centimeter per second. So it is gram centimeter per second. So it is the unit of momentum. Now the very important thing has come. Is the momentum of a body is constant? Definitely we will tell no. If the velocity of the body changes, then the momentum of the body also changes, right? So our next target is to learn about change of momentum. Okay, let's see. See, it is very interesting thing. Okay, don't be bored. This part is very interesting. So next target is to learn change in momentum. So momentum means the linear momentum. So we are not using the linear word continuous. So we are using just what? Momentum. So change and momentum we represented by delta P. This delta stands for change. So delta P is equals to definitely delta m into V. Delta P, that is the change of momentum, that is equals to delta m into V. And now you can say, sir, mass of a body cannot change. We all know. So delta P, we can write m. M is constant for a body. We know that, into delta V. I am telling yes, it is right, but it is wrong also. Now you can ask, sir, why it is wrong? Now I am telling, we have taken in our general classical mechanics that mass of a body is constant. But the great scientist Einstein has given a very interesting theory which is known as theory of relativity. So theory of relativity, it is based on, means I'm not telling the whole theory of relativity now, it is not possible. But here the main thing is mentioned that in this theory of relativity we have taken the speed of light is ultimate. That is, the speed of light, that is not denoted as c, whose value is 3 into 10 to the power 8 meter per second, that speed should be taken as the maximum speed attained by a body. No body can able to move more than the speed of light. Einstein has told, if a body moves nearer to the speed of light, and if the speed is v, if the speed of body v is comparable to the speed of light, then the mass of the body change with the speed. Now you may ask, sir, it's a total new thing for us. Yes, definitely it is a new thing for you, but I don't want to go more deeper in that because it is not needed now. Here, one thing you have to remember that I have written here, that if a body moves, so is it possible for a body to move with a speed almost with the speed of light? It's impossible. But if it moves, who can able to move it? It can be moved by subatomic particles. Subatomic particles. So subatomic particles are whom? Like electron, proton, neutron. Okay, so if I am talking about these particles and they are moving almost with the speed of light, and this case the mass of the body can be changed with the speed. How it is changed? It is changed by forming an equation, and the equation I have written here, that m equals to m0 c square by m0 into, not c square, 1 minus v square by c square. So you can ask, sir, from where this equation has come? I have told one thing, no need to give more focus on that. Simply you see one thing, that if the body moves with a speed of velocity v, which is comparable to the speed of light c, see here, c is written, then the mass of the body is changes with this equation, that is m0 by root over 1 minus v square by c square, where m0 is known as static mass. Static mass means when the body is in static, that time its mass, and m is the mass when it moves with a speed of v. Okay, now if a body moves with a speed of v, which is comparable with the speed of light, in that case, whenever we have to write about delta p, that should come delta into mv, this one. Why? Because here m is not constant, that m is also changed with the velocity. Now the question has come, sir, what is the need of this thing here? No need. It is only possible for the subatomic particles. As is we discuss about the subatomic particle? Are we discuss about the subatomic particles? No. What we have discussed? We have discussed about the simple thing, that is Newton's second law of motion, which is totally a part of classical mechanics, and where v is very less than c. v is very less than c. So m is equal to or almost equal to, we can say that, m0. So here mass is not changed. So we can say that in this case, in the case whatever the things we have discussed now, in every case the mass of the body is constant. So we can say change of momentum equals to change of velocity, not change in mass. Now you may ask, sir, then what is the need of this whole thing? I'm telling it is only for your knowledge. From here no question will come. From here no question will come. We have only discussed to show you that if velocity is nearer to the velocity of c, then the mass of a body is changed. If it is not, then we can neglect it. Okay, so m equals to m0, and that means change of momentum is equals to mass into change in velocity. I have written here change in momentum is equals to mass into change in velocity. So don't be panicked by this portion. If you want to leave that portion also, no problem. If you think it is too hard to understand, just skip the video and go to the next part. Okay, I think it is clearer to you. We have discussed about change in momentum. Now we will see derivation of change in momentum. So in the previous part I have already told change in momentum means mass into change in velocity. Let's see. Okay, assume a body of mass m is moving with a speed of u. Okay, a body of mass m is moving with a speed of u, and a force F is applied on it. Okay, a force F is applied on it, and for that reason, after time t, the body will get a velocity v. Simple thing. The mass of the body is m, it is moving with a speed of u. A force F is applied on the body, then after time t, the velocity of the body changes to v. So from here we can say mass equals to m, initial velocity equals to u, final velocity equals to v, force is equals to F, time is equals to t. Okay, so that thing is given to us. And now if it is told to us that what will be the initial momentum, what will be the initial momentum? We know momentum is equals to mass into velocity. So mass is m and initial velocity is u. So initial momentum pi is equals to m into u. What is the final momentum? Final momentum, that is denoted by pf. So mass, I have already told, mass is constant. Here in classical mechanics part, what we have discussed, classical mechanics means where we have discussed about the motion of a general body. Okay, that is classical mechanics. And when we have discussed about the motion of the subatomic body, the smaller body like electron, proton, neutron, etc., then it is called quantum mechanics. Okay, so final momentum pf equals to m into v. What will be the change in momentum? So change in momentum, that is equals to pf minus pi. Always change can be calculated from final minus initial, that is pf minus pi. So pf minus pi means mv minus mu. If I have taken common, so m into v minus u. Okay, so earlier we have written that del p equals to m into del v. Del v is what? It is change in velocity, and that is here also the same thing, m into v minus u, that is change in velocity. Now how much time it will take to change the momentum? And yes, the time is taken, it is t. Okay, t time is taken to change the momentum. Now the question has come, what is rate of change of momentum? Rate of change of momentum, that means change of momentum per unit time, then it will be m into v minus u by t. Okay, so in t time the momentum is changed m into v minus u. So rate means per unit time, so we have to divide it by t, that is m into v minus u by t. Again, we know one thing. We know that v minus u by t is equals to a. What is it? It is acceleration. So from here we can write rate of change of momentum is equals to m into a. That is mass into acceleration. Mass into acceleration. It's a very important calculation, that from here we have got the rate of change of momentum is mass into acceleration. What is the physical significance of it? Let's discuss. What is the physical significance of rate of change of momentum? Let's see. If you have not copied it, pause the video here, copy the thing and then move forward. Okay. Physical significance of rate of change of momentum is equals to mass into acceleration. See, now the question has come, why the momentum is changed? If I am asking number one question, why the momentum is changed, what will be the one word answer? The one word answer is due to application of force. Due to application of force. Achha, when we have applied force, what we have seen here by the statement, that is rate of change of momentum equals to mass into acceleration, that due to the application of force, what thing is changed? Now velocity is changed. That means velocity is changed, and we know that rate of change of velocity is equals to acceleration. That means by the application of force, I provide acceleration to a body. Why? Because due to the application of force, the velocity is changed. As we know, that velocity is rate of change of acceleration is rate of change of velocity. That means acceleration comes to a body due to the application of force. So we can conclude that acceleration is directly proportional to force. Why? If you apply more force, the acceleration will more change. What is the reason behind it? Now, as you apply more force, the velocity will change more. And as the velocity will change, acceleration has come. So, acceleration is directly proportional to the force. Okay, so if I want to represent it graphically, so along x-axis, which is independent, that is force. So you can able to change the force, and by the application of force, what thing has come to the body? Acceleration. So along y-axis we have taken acceleration. So if I have drawn the graph, that graph should be looking like this. It's a straight line, and it represents as we apply more forces, the acceleration will be increased. What is our target? Our target is to measure the force. So it is the first step what we have seen here, that by the application of force I can able to change the acceleration. Okay, next thing, Okay, so I think this portion is clear. That is the physical significance of mass into acceleration. One more thing is left. What is it? So it is the first part, that is for acceleration. Second part is that when we have applying force, is it same that if I am applying force, the acceleration will be achieved by the body for different bodies, it should be same? I'm just clearing the concept, what I'm just want to tell. My point is, if I apply same amount of force for different bodies, can they will get same amount of acceleration? Then you say, no, it is not possible. Why? Now, if you apply a force for a body of mass 2 kg, as an example, if you apply F amount of force, if here the acceleration is A1, if you have taken a body of mass 5 kg and you have applied same amount of force F, then your acceleration is A2. So is this two acceleration is same? You will say no, more mass, so here the acceleration will be less. If you want to give a blow to a thing whose mass is less, so it will move more distance. If it is too heavy, so it will not much move. Okay, so it is clear that acceleration 1 is greater than acceleration 2. That means not only by application of force will get that acceleration, it is not true. Along with that, one important thing is there, that is mass. Okay, more mass, less the acceleration. More the mass, less the acceleration. Okay, so here we can say that force depends on mass. If the mass is more, so you need to apply much amount of force. If your mass is less, so by applying less amount of force, you can able to get your desired value of acceleration. So if you want to draw it graphically, so that along x-axis I am taking mass, along y-axis I am taking force, because here mass is an independent variable and force is a depending on the mass. So here also the graph seems to be looking like this. There we have seen two equations. One, acceleration is directly proportional to force and force is directly proportional to mass. If I have taken, this is equation 1 and this is equation 2, together we get an equation that is F is directly proportional m into a. F is directly proportional m into a. M into a means rate of change of momentum. So we can write force is proportional to rate of change of momentum, because we have already learned the mass into acceleration, that is m into a, that is equals to rate of change of momentum, and force is coming the same thing. And by that, Newton's second law of motion has come. Now I just want to write the statement. What is the statement of Newton's second law of motion? The second law of motion, okay, what it states? Newton's second law of motion. Newton's second law of motion states that the rate of change of momentum is directly proportional to the force applied on a body and the momentum is changed in that direction in which direction force is applied. So it is Newton's second law of motion. What it tells? The rate of change of momentum is directly proportional to the force applied on a body, and the momentum is changed in that direction in which direction the force is applied. See here, we have just proved that the force is directly proportional to the rate of change of momentum. That is, F proportional to m into a. Okay, now see, now we have to make a equation, otherwise we cannot able to get any sort of value of force by the help of mass and acceleration. Okay, so for that reason, you see, we have derived another physical quantity called momentum only for that reason. Okay, see, F is proportional to m into a, so we have to take a constant k. Okay, so where k equals to constant. Now what will be the value of constant? How do we know? For that reason, we have taken one trick. If m equals to 1 and a equals to 1, then experimentally f is also equals to 1. What does it mean? It means if you take a body of unit mass and if you have to move it by unit acceleration, then you need to apply unit force. That is experimentally shown. And now you can say, just show me the experiment. I cannot able to give it to you. Okay, so experiment, I cannot able to show it here. That is done by the scientist earlier. So here, if I put that all values, so k equals to coming 1. So k is a constant whose value is 1. So if I put the value of k here, the equation has come. F is equals to m into a. That is the measurement of force. By taking a product of mass and acceleration, we can able to measure the force. That is Newton's second law of motion. Okay, so for that reason only we have derived so much things. So we want to find this equation. By that we can able to measure the value of force on a body. Okay, now as this has come, so we have to go for its unit. If F equals to m into a, then what should be the unit of it? What should be the graphical representation of it? So let's see. Okay, so unit is a unit. F equals to m into a. We have already shown it. Okay, so unit should be the unit of mass, that is kg. Unit of acceleration, that is meter per second square. So unit of force, SI unit of force should be kg meter per second square. That is given by a new name, that is Newton, which is symbolized by capital N. Now you may ask, sir, why Newton is in small letter? Simple thing, you all know, whenever we have to show a unit by the name of the scientist, that should be in small letter. When it will be the name of the scientist, that should be in capital letter. So you all know that thing. CGS, gram centimeter per second square. So here this is known as time. Okay, this is known as time. So two units are there. One is Newton, first another one is time. So if anyone asks you, what do you mean by 1 Newton force? What do you mean by 1 Newton force? So 1 Newton means 1 kg into 1 meter per second square. That's now we have seen here. 1 Newton equals to 1 kg per 1 meter per 1 kg into 1 meter per second square. So what should be the definition? That if 1 kg of mass is moving with a acceleration of 1 meter per second square, then the force applied is 1 Newton. That means 1 Newton force is a force when it applied to a body of mass 1 kg, it will get an acceleration of 1 meter per second square. If I am talking about what do you mean by 1 dyne force? So very easy. 1 dyne means 1 gram into 1 centimeter per second square. So simple thing, mass of 1 gram, it is moving with the acceleration of 1 centimeter per second square, then the force should be 1 dyne. That things I have not written here, you will see it from the book. Okay, so 1 dyne of force is that when it is applied on a body of mass 1 gram, then the acceleration is 1 centimeter per second square. Okay, I think this is clear. Now when we have to discuss about the relation between these two units, it is very important. You have done it earlier also. 1 Newton is equals to 1 kg into 1 meter per second square. Now if I want to change it in dyne, so 1 kg should be converted, should be gram, so 1000 gram into 1 meter should be converted into centimeter, 100 centimeter per second square. Second square is same, so it is 10 to the power 5 gram centimeter per second square, that is 10 to the power 5 dyne. So 1 Newton is equals to 10 to the power 5 dyne. Okay. Next thing, graphical representation of this equation. Graphical representation of this equation. I think this part is clear to you. Graphical representation. Let's see how we can able to represent it graphically. Graphical representation. So graphically, whenever we have to represent it along x-axis, see, we all know the equation f equals to m into a. So a should be taking along y-axis and x should be taking along m should be taking along x-axis. The reason is that m is constant, but a can be variable for different mass. So how this graph look? The graph should be looking like this. Okay, and where it is mentioned that f is constant, that f is not changed. The product of mass and acceleration is constant. If you increase the mass, okay, acceleration will be decreased. That's why you see when the mass is more, in this point the mass is more, but you see the acceleration is less. If you just decrease the mass, if your mass is decreased, your acceleration will be increased. See, so that special kind of graph, it is known as hyperbola. Okay. Okay, so this is known as hyperbola. Okay, that is the graphical representation of Newton's second law of motion. Okay, what extra thing we can do from here? Now, as we have derived the Newton's second law of motion, we can we able to return to Newton's first law from Newton's second law? See, let's check it. Okay, so our next target is Newton's first law from second law. See, in class 9, this concept is correct. In class 9, if anybody asks you, can you able to get Newton's first law from second law? Yes. But later, whenever you have to come to higher physics, okay, then if anybody asks you, can you able to get Newton's first law from second law? It is totally wrong. We cannot derive Newton's first law. It can be arrived only. We cannot derive it. Derived and arrived, two different things. We can reach in that point. We can think that, but we cannot derive it. But for class 9, it is okay. You can do it. Okay. Why it is not? So that is some another reason is that. Next. F equals to M into A. A means we know A equals to V minus U by T. V minus U by T. Right? So here, if I just want to say that I just want to reach in Newton's second law, so that means as per Newton's first law, if no force is applied, then the state of rest of or motion of a body remain same. Okay, that we have learned that if you have not applied any force, then the state of rest or motion that of a body should remain same. It shouldn't be changed. So here F equals to M V minus U by T. So if F equals to 0, if F equals to 0, then you see M into V minus U by T is equals to 0. T, if you multiplied and F, it is gone, it is 0. So V minus U, that is 0. That means V equals to U. What does it represent? It represents if no force is applied, then final velocity should be initial velocity. And that is the story of Newton's first law, that if you are not applying the force to a body, if the body is in motion, that will remain move with same velocity in same direction. It is shown here. And here if I have taken that if u equals to 0, u equals to 0 means the body is in rest. U equals to 0 means the body is in rest. So if U is at rest, then V is also 0. Okay. So if you are not applying the force to a body, as initial velocity and final velocity is remain same. So if the body is at rest, so the final velocity is also rest. That means no velocity is changed or no increase or decrease of velocity if no force is applied on it. So this is Newton's first law from second law. Okay. Now we'll go for some natural examples of Newton's second law of motion. Okay, some natural examples of Newton's second law of motion. It's very interesting examples are there. You can able to correlate with yourselves. Okay. Example. So example number 1. What is that? A cricketer pushes his or her, definitely it can, cricketer can be a girl also, pushes her hand back during catch a ball. So it is a very clear thing. Whenever we are talking about the catching of a ball, okay, so we generally push our hand back by receiving the ball. Okay, we catch the ball by this way or this way. We catch it, we make our hand closer or make our hand down. Why? Whenever someone is taking the ball, nobody has catch the ball like this. Everyone catch the ball and push it back to himself or herself. What is the reason behind that? The reason is that whenever the ball is coming to the hand, it is applying a force. Okay, when the ball is coming to the hand, it is applying a force. Initially, assume the ball is coming to you by the velocity. The batsman is hit at the ball, assume it is u, that is the initial velocity of u. Okay, and assume the mass of the ball is m, and when it catching by u, then its velocity is 0. So we can say in hand final velocity v equals to 0. Okay, now when we are talking about force, we know the equation F equals to m into a. M into a means m into v minus u by t, right? Here you see v is 0, so m into 0 minus u by t. Now it is coming minus m into u by t, right? Now what will be the mass of the ball? That is not depending on you, that is already fixed. Okay, in which speed it will come to you, you will not tell the batsman that you just beat the ball with a less speed, because he will try to beat it hard, so you also not controlled by you. T, it's a very interesting thing. T, T means the time. The time when the velocity is changed. The time when the velocity is changed from u to v. So if I increase the time, if the time of change of velocity is increased, then force should be decreased. Simple thing. T is in denominator. See it here. T is in denominator. So if you increase T, the velocity should be decreased. So how do you increase T? To make the ball just push back. So as you push the ball back, you will take more time to catch the ball. As you have taken more time to catch the ball, then the force will be decreased because the denominator is increased, and that's why we catch the ball. Now the question has come, why the minus sign has come? What is the reason behind that? The minus sign is that you just want to make the speed of the body 0, and as the ball is coming towards you, the direction of force is here, and for that reason you are applying an opposite force to make the body or make the ball 0, so that that force should be equal and it will be opposite to the force coming to the ball. So this minus sign represents the force applied by cricketer is opposite to the force of ball. Simple thing, force of ball is coming in this way. You have to apply force in opposite direction so that it will be balanced, the velocity will be zero. Idea is, if you take much time to catch the ball, then the force is applied on your hand, it is less. So you know that those who are playing cricket, when you are taking the catch like this way, you will not feel any force at your hand. But if you want to force directly, it is coming to your hand suddenly, then your hand is sometimes very hard. Okay, so this thing is the example of Newton's second law of motion. Okay, not only that, if you read the book, many more examples you will get. Okay, number two example, you see, whenever if I'm talking about a glass vessel or a glass, okay, when a glass vessel, number two, if I have to, that glass vessel is fallen down on a floor, it breaks, but it doesn't break in sand. Simple thing, if you fill a glass vessel on a floor, so after heating here, okay, you see it will break. But if you fill over the sand, so it will move inside the sand little bit and it will not break. Okay, what is the reason behind it? The reason is also very same. Okay, what is that? Simple reason. F equals to m into a, that is m into v minus u by t. When it coming downward, if I am taking its initial velocity is u, when it coming to the ground, then final velocity, okay, final velocity v equals to 0, because after coming downward it just changed the velocity, so the velocity is 0, and here f equals to minus mu by t. So if t is more, f is less. If the time to make the velocity 0 it is more, okay, then your force is applied on the glass, that should be less. So for the case of a concrete floor, when it reaches, suddenly the velocity goes to 0. So much force is applied, it suddenly breaks. But when it reaches to the sand, so it will just move inside the sand a little bit. So as it moves inside the sand little bit, so that's why it will take much time to make its velocity 0. So that's why less force is applied and it is not break. Okay, simple thing. Not only that, when, if I'm talking about the third one, that an athlete, a long jumper or a high jumper, when he jumps or she jumps, they just want to fail on a sand, okay, soft sand or carpet or sponge. Okay, usually whatever we have seen, a high jumper or a long jumper jumps on sand or sponge or carpet. That means a very soft surface. What is the reason behind it? The reason is that simple thing. When you just reach on a soft surface, then it will take much time to make your velocity 0. If you just fall on a floor, suddenly your velocity comes to 0. But if you just jump on a soft surface, then it takes much time to make your velocity 0. And for that reason only, you will not be wounded. Otherwise, if you suddenly fallen down on a concrete floor, suddenly your velocity going to be 0 and you will be injured. Okay, So all that thing, these are the examples of Newton's second law of motion. Okay, hope you can able to understand it. So see the video. If any doubt, inform me. Thank you.